I'm going to start very briefly talking about a couple of the things that I covered in my talk last year, just for anyone who wasn't here. So I'll talk briefly about the process for requesting Apollo samples for allocation, and I'll talk then a little bit about the curatorial facilities that the samples are stored and processed in where I work. And then the bulk of the talk will go into a very special display cabinet that we have inside our curatorial facility. And I'll talk about some stories and background on different rocks that are on display there. So first off, this right here is Building 31 North, just across the street a bit. That is where the Apollo samples are primarily stored and curated today. That wing of the building was built specifically to house the Apollo collection in 1979. Prior to that, it was originally in the lunar receiving facility, Building 37, which was demolished last year, and then in the main Building 31 until 31 North was constructed. All right, so this is the basic process for requesting scientific samples for allocation. Just go to our website here, and it has a lot of detail on how you go about making a request. And these samples can be allocated for research, education, or public display purposes. Any request that is submitted gets reviewed twice annually by an external scientific review panel comprised of lunar sample scientists who are very well versed in the different types of lunar research that are being proposed in the different submissions. And they make recommendations to NASA headquarters, who then make final decisions on what requests get approved, and the ones that do get approved are then overseen by our curator, Ryan Ziegler, and he essentially delegates the processing and work to myself and other colleagues of mine who are the ones that get to then be hands-on with the samples, so to speak, in order to prep them for the needs of the particular allocation that they've been approved for. Research and education samples do have to be returned to our facility after the work has been completed, whereas public displays are typically considered to be kind of a semi-permanent most of the time. They can be recalled. That is possible and has occasionally happened, but it's uncommon. All right, so this here is a couple of photos of our facilities. So the top left photo here is the inside of our vault, where the samples are primarily stored in the long term. So we call it our pristine sample vault. It contains 18 of these nitrogen purged cabinets. Each cabinet has rows and rows of trays that are all sealed, and then those trays have many different samples inside of them that each have 3 layers of individually sealed nitrogen containment on each one of them. So there's a lot of careful redundancy to keep the samples safe so that they don't ever get exposed to Earth's atmosphere, where they would begin to oxidize and otherwise be chemically altered. We also have 3 special cabinets in the back. You can't really see them in this photo, but we call them our rack cabinets, the restricted access collection. It's just a handful of samples that are especially fragile and crumbly, and we set them aside separately so that as we are going through our normal cabinets to pull samples out for allocations, we're not bumping them and causing damage to them. So when samples do get approved for allocation, they then get transferred out of the vault and into our main processing lab, which is in this other photo here on the bottom right. In that lab, we have 8 further nitrogen cabinets which are designed for sample processing work, where we do subdivisions of the samples. So there's a lot of soil samples where we can do scooping and subdivision. We can also break and cut the rocks into pieces inside these cabinets and document our work using these special ports on the side and microscopes and such. These cabinets are also dedicated to specific missions only. We don't mix the missions in the processing cabinets because we don't want to risk cross-contaminating samples. The missions did land on different locations on the lunar surface with different local geology and geochemistry, so getting a little bit of dust from one sample onto another one could potentially cause some problems for future research. So for instance, this cabinet here is only for Apollo 16, this one is only for Apollo 17, that one's only Apollo 14. But we do also have a display cabinet in the lab, and that's what I'm mostly going to be talking about for the rest of the talk here. And this is it right here. So this is a beautiful display cabinet. It has 5 very large samples on display, and these samples are representative of the different types of rocks that are found on the lunar surface. This is, in fact, the world's largest display of moon rocks in the world by mass, totaling about over 25 pounds or 11.5 kilograms. And this display cabinet does, in fact, break our rule of mixing missions that we have in the other cabinets back here. So there are 5 rocks on display from the 3 last Apollo missions, 15, 16, and 17. But this cabinet is only for display purposes. If we needed to do any work on these samples, they would have to be packaged up and transferred out into one of the appropriate processing cabinets for its mission in order to do that work. So you can see in front of each one of these samples there's a plaque with a number. That is the sample's official name. The first 1 or 2 digits represents the mission that it came from. With Apollo 11, they weren't thinking in advance how they were going to integrate them with future mission numbering schemes, and so they started with 10 instead of 11. With Apollo 12, 14, and 15, they did actually start with 12, 14, and 15, and there are 2 Apollo 15 samples on display here on either end. And then with Apollo 16 and 17, they changed the numbering scheme again. They decided they needed an extra digit in there to represent more information about what type of sample it is and where it was collected during the mission. But they didn't want to change the number from a 5-digit number, so they dropped the 1 off the front and it just starts with a 6 and a 7 instead. Not a consistent numbering scheme at all, but there's only 6 missions to keep track of so far, so it's not too bad just yet. You'll also see that there is a cube next to each one of the samples. Those cubes serve 2 important purposes. So these are all 1-inch cubes, so they can be used for scale. We also have 1-centimeter cubes for smaller samples. But more importantly, the faces of the cubes are labeled with orientations: north, south, east, west, top, and bottom. It's showing you the orientation that the rock is in as you're looking at it with respect to how it was actually collected on the lunar surface. The astronauts documented most of the rocks in place before they picked them up, and so we know what their orientations were. And we try to maintain that orientation for as many of the subdivided pieces over time as we possibly can. That is information that is very important for certain types of research. Now I'll go through and talk about each one of the rocks specifically, and we'll start here on the left and work our way towards the right. So that first rock on the left, that was from Apollo 15. It was the first mission where there was a rover on the surface. And the rover, well, that was built by Boeing. So back in the 1970s, Boeing was in fact in the business of making very small electric cars for the moon. It only weighed 208 kilograms or 460 pounds on Earth, which was only 34 kilograms or 76 pounds on the moon. Very, very light. But it was incredibly useful because it allowed for a much wider range of travel, faster travel on the surface of the moon compared to the previous Apollo missions where everything was done on foot. And it also allowed carrying more equipment, more scientific instruments, and collecting a larger volume of samples than they were previously able to do. Now here's a map of where the lander was at, and then 3 traverses that they took with that first rover on Apollo 15. And those traverses collectively covered about 17 miles or 28 kilometers over a course of 18 hours between all 3. But they were not allowed to travel out more than 5 kilometers or 3 miles from the landing site. Just in case the rover broke down, they would still be close enough they could walk back. Makes a lot of sense. And so what they would do is they would drive out to the farthest place that they were going to sample from and then work their way back. And so they were going out doing these traverses, and then the final one was this one in the middle here. They first drove out towards this shadow from being cast by this big ridge, and then hugged that shadow, came out down this way, and then eventually Mission Control lets the astronauts know that they've been out long enough, their oxygen reserves are starting to get low enough that it's time to pack up and head back to the lander now. Their EVA is over. Well, being good astronauts, of course, they comply. They get on the rover, they start driving back, and then when they get right about to where this red arrow is at, Mission Commander Dave Scott, he was the one driving, he looks off to the side and he sees this rock just laying all by itself in the middle of nowhere that he just absolutely loves. And he knows that the scientists back home would love it because it looks totally different, he feels, than anything else that has been collected so far. But he also knows that because Mission Control already told them that the collection process of this EVA is over and time to head back, they're not going to give him permission to stop and get it. So what he does is he radios Mission Control and stops the vehicle and tells them, I'm having a problem with my seatbelt, I need to stop briefly and fix it. Meanwhile, his partner was the one who had the live video camera. Without a word between them, he just turns the camera the opposite direction and starts talking. Talking. The way that their radio communications worked was one way. If the astronauts were talking, Mission Control couldn't talk over top of them and give them new orders or ask what's taking so long or anything like that. So as long as he kept talking, it's all good, right? So Dave Scott gets off the rover and quickly goes and collects that sample, puts it in a pocket on the leg of his spacesuit, and then climbs back on and announces, all right, my seatbelt's fixed. We're going to continue the rest of the way back. And as far as Mission Control knew, that was exactly what happened until they returned back to Houston, where all of the samples were then being inventoried. Well, there were, of course, logs that Mission Control had kept of everything that had been collected over time, and they found this one big rock in the collection that wasn't in their logs at all. Well, they asked Scott about it, and he was like, oh yeah, that one. So remember on the way back when I had that seatbelt issue? Yeah, I have a funny story to tell you about that one. And so we call that the seatbelt rock. It is a, geologically speaking, this is a basalt. It is a volcanic rock. It is believed to have formed over 250 kilometers below the surface of the moon, or have formed from a magma that originated at that depth, which then rose up to the surface and erupted on the surface of the moon and had a huge volume of dissolved gases within it that were all bubbling out. But the rock cooled off before all those gases could escape, and that is why it has all these bubbles, these holes in it that kind of trap those bubbles in place. And this right here is the largest remaining piece of it today. It's about a third of the original total mass. And of course, all of the rocks that are on display, they are the largest remaining piece, but they're not the only remaining piece. We have smaller pieces that we use for allocations and that kind of thing, which are available, and that way we don't have to mess around with these display pieces. So it's sitting on a flat side that's been cut on our bandsaw, and this is one of the most prominent rocks in our collection because of that story that goes with it, and it really is a great story. So moving on to the next sample, 60015. This is what is called an anorthosite rock. It was originally 12 pounds, 5.5 kilograms, quite a large rock as well. And it's coated in a thick layer of blackish brown glass. You can see a little bit of rock that's peeking out here. It's all white in color. And that white rock is a rock type called anorthosite. The presence of a northocite in the Apollo collection is what led to the modern theory of how the moon formed. So prior to Apollo, it wasn't really known how the moon formed. It was thought maybe the Earth was a passing the moon was a passing asteroid that was captured by the Earth's gravity, or maybe very early in the solar system's history, the Earth was spinning much more quickly and a blob flew off of it that became the moon. But neither of those primary theories could explain how you get large amounts of a northocite, because a northocite takes very unique conditions to form in nature. There's a little bit of it on Earth, but it's quite rare. And the reason it's so unique is because it's composed almost entirely out of just one single mineral called anorthite. So you have to have some kind of large-scale process that's concentrating huge volumes of one mineral together to form a lot of rock. And that is where the giant impact theory comes into play, where it would explain how you get that anorthocite. It states that early in the solar system's history, there was an object roughly the size of Mars that collided with the Earth in kind of a glancing blow. And it launched a huge volume of debris into orbit around the Earth in a disk that then coalesced to form the moon. And when that material first came together, it still would have been so incredibly hot from all the energy released in that collision that it would have been essentially an ocean of magma orbiting the Earth thousands of kilometers deep before there's any solid material below that. And probably the entire Earth would have been molten as well from that impact. So anyway, over time that magma ocean starts to cool, and as it cools, crystals start to form within it. Those crystals have different compositions, different densities. The heavier, denser crystals tend to sink down to the bottom, and the lighter ones float up to the top. And the lightest mineral in abundance on the lunar surface is anorthite, the mineral that makes up that white rock, anorthocite. So what would have been happening is slowly over time, this mineral is floating up to the surface of the magma ocean and collecting and forming these icebergs of rock that are growing bigger and bigger over time until eventually they cover the entire surface of the moon in its original primordial crust. And when we age date the Apollo samples, these anorthocite samples are in fact the oldest in the collection. They're about 4.4 billion years old, most of them. This one here on display is within margin of error the oldest rock in the Apollo collection. And just for reference, the solar system is about 4.5679 billion years old. So it's quite, it's almost as old as the solar system itself. It formed very early. And then the surface of this rock, that black glass coating, that is incredibly young. That is formed by a meteor strike that hit the moon's surface and flash melted surface material that then splashed and covered over existing rocks in the area, coating this rock here in that molten material that then quickly quenched and formed a black glass. And so that is dated to be about only 2 million years old, which geologically speaking is nothing, which means this rock is incredibly special because it essentially comprises the entire geologic history of the moon that is recorded in the moon's rock record. The third rock here, this is Apollo 17 sample 70017. This is another basalt, another volcanic rock. And this is believed to be one of the last, well, it is one of the last rocks that was collected on Apollo 17 and possibly the last one. There's a little bit of uncertainty in the records which of the last 2 or 3 was actually last. But this was collected by Jack Schmitt, the only geologist to go to the moon. And when he collected this rock, or when it was brought back to Earth, it was subdivided up and about 1 gram was given to every country that existed in the world at the time as a goodwill gesture, as well as a piece being given to each of the 50 US states. And this was in fact the second goodwill sample that was given out. There was a similar gesture given out from Apollo 11 soil samples as well. So every country in the world should have gotten 2 lunar samples from the Apollo missions, at least at the time, countries that existed at that time. This is just an example here of Belgium's Goodwill sample of this 70017 rock, which we call the Children of the World rock. And I'd like to read a quote here from Gene Cernan, who said this from the lunar surface as Jack Schmitt was collecting the rock. So he said, "It is a rock composed of many fragments, of many sizes and many shapes, probably from all parts of the moon, perhaps billions of years old, but fragments of all sizes and shapes and even colors that have grown together to become a cohesive rock, outlasting the nature of space, sort of living together in a very coherent, very peaceful manner. When we return this rock, or some others like it, to Houston, we'd like to share a piece of this rock with so many of the countries throughout the world. We hope that this will be a symbol of what our feelings are, what the feelings of the Apollo program are, and a symbol of mankind, that we can live in peace and harmony in the future." And so we call that the Children of the World rock. This is about half of its original size. Most of the remaining portion was subdivided up and given away. We do still have some remaining pieces of it as well for scientific availability. But this is a really important rock for that kind of historical purpose. And Jack Schmitt, who collected the rock himself, being a geologist, he is still to this day doing active scientific research and comes to the lab occasionally. And he's very happy that this is a rock that we still have on display. The fourth sample here, this is the largest sample that was collected by any of the Apollo missions. It was originally almost 26 pounds. It was over 11 kilograms. And the astronauts named this after the geologist that taught them their geology, named William Mulberger. He was also the leader of the Apollo 16 field geology team and the principal investigator for their mission. It is considered to be an impact melt rock, which would have been formed by a fairly large meteor impact into the surface of the moon that melted a large volume of material that then slowly cooled and formed a new rock that had other pieces of pre-existing rocks entrained within it, including a big chunk of that white anorthosite that was sticking out of it. And that chunk of anorthosite is what made them want to collect this sample. In fact, Bill Mulberger was watching the live video from Mission Control and helping direct which samples he thought they should collect. You can see it here kind of compared to the scale of an American football. It's almost the same size. The collection of this sample was quite difficult because it was far bigger than the collection equipment was designed to collect. So they couldn't just bend down and pick up a sample. The spacesuits didn't have that kind of dexterity to them. They could bend down about that far, that's it. And the tools that they had, they were only designed to pick up mostly samples that were like fist size and smaller. The only reason they were able to successfully collect this rock is because of where it was located, right on the lip of a big crater called Plum Crater. And astronaut Charlie Duke was able to stand just below the lip and bend over on one leg and slowly roll the sample towards himself and up the side of his leg with his fingertips until he could get a grip on it and pick it up in order to bag it and stow it away. And there is live video of that being collected, and it's pretty funny. He has a quote as he's collecting it. He says, "If I fall into Plum Crater, Mulberger has had it." So here's the largest remaining piece. You can see a little bit of the anorthosite cap here. Most of that has been removed today and subdivided up. This rock is also interesting because it's covered in little micrometeorite impact craters called zap pits. And then the final rock here, just to wrap up, is sample 15459. It is considered a regolith breccia. So regolith is the unconsolidated dust and rock fragments covering the surface of the moon, caused by billions of years of impact bombardment, kind of mixing things together and scattering them around. Today there's a layer that's several meters deep covering almost the entire surface of the moon. And every once in a while, a smaller impact hits that regolith, and the shock force of that impact doesn't melt it, but it's enough to compress it and heat it up enough to sinter the regolith in that area like a brick and form a new rock out of it like that. The geologists, the astronauts decided they had a better name for it than regolith breccia. They wanted to call it instant rock for that reason, and kind of described right here in the transcripts. Jim's given a lovely clear description of it here. If you've got enough regolith and an impactor of the right size and velocity, you create instant rock. And I'd like to finish off here just showing a little bit of our record keeping. So this is as that rock was being bandsawed in 1985. You can see it was being lined up on the bandsaw, so you can see where the cut was going to go through before the cut was started. And then as the cut is being made, every time a piece breaks off, you have to stop the cut and document that piece. Show exactly where it fit back on and document it from multiple different angles before you can resume the cut. And then you do it again every time that happens until at the end you have to piece everything back together like a jigsaw puzzle. This is very slow and time-consuming and a meticulous process, very detailed, lots of records kept. Today everything is digitized, but we still keep paper copies of everything as well, so these are from 1985. And that's very important information for scientific purposes to know exactly where one piece was allocated versus another and how they relate to one another. And I'm probably about out of time, so I'll just say that our display cabinet is really one of a kind. There's so many stories that can be told about the samples that are on display in it, and I would really strongly want to point out that here at Space Center Houston, right around the corner, we have another display with 4 other large and unique Apollo samples. And I highly encourage everyone during a break or maybe during the Space Center Houston tour, hopefully it goes over there and people get a chance to look at it. So thank you very much.